All right. Good afternoon, everyone. My name is Cathy Cheng, and today I'll be presenting on my senior design project titled the Autonomous Water Condition Understanding Apparatus, better known as AWCUA. Okay, so I'm a part of an interdisciplinary team. We span electrical engineering, mechanical engineering, mathematics, and biology. And from left to right, we have Ava Remler, Fallon McBrien, myself, and Charles McGinn. And our faculty advisor is Professor DeBella, who is in the audience today. So I'll begin with a little bit of background about our problem. So here in Boston, especially at BU, we are lucky to be situated right next to the Charles River. And like many other rivers, we depend on the Charles River for access to water, as well as transportation and recreational activities. But every summer, we see patches of green emerge on the top of the river, and what these are algae blooms caused primarily by cyanobacteria, also known as blue-green algae. And while this is a very natural occurrence that regularly occurs in river ecosystems, they can become harmful. And in those cases, they are known as harmful algae blooms or HABs. And when they are harmful, they can introduce toxins to the environment and also to our bodies. They can also block sunlight from photosynthesizers below the surface of the water. In humans, they can cause respiratory illnesses as well as gastrointestinal illnesses. And they can also deplete oxygen as these algae use up oxygen in that environment. And in more severe but very rare cases, they can also cause paralysis and death in humans. So as we can see, this is a very severe problem. So what is currently being done about it is we have a variety of control mechanisms ranging from mechanical to chemical to biological. We also have a variety of prevention methods such as reducing nitrogen and phosphorus runoff from agricultural sources, as well as minimizing invasive species. But in order to do all of this, we need to know when and where these algae blooms occur, and that is why it's so important to monitor these blooms. So in order to do that, we have been working with our stakeholder, the Charles River Watershed Association, also known as CRWA, and their mission is to identify and remedy chemical pollution in the Charles River, and they do that by conducting monthly water sampling at the edge of the river through a system of volunteers. And one of my team members, Charles, and I were lucky enough to attend and help out at one of these sessions. And basically, they take a sample of water along the entire 80-mile span of the river and then drive that sample to the nearest laboratory testing facility. So a little bit more about that and some existing methods for detecting whether or not cyanobacteria is present in a water sample. So the first one is laboratory testing, which is what the CRWA does. Another one is satellite imaging, which is fairly popular. And we also have this technique called UV visible or UV vis spectrometry, which I'll go more into depth about later on. But the problem with these existing methods is that, number one, they are extremely expensive, and number two, such as with satellite imaging, they can be very inaccessible to the general public. So just to break down the cost a little bit further, with some commercially available models of sensors, they can run up to about $2,000. Additionally, for the sampling methods, the laboratory sampling methods, these run about $340 per test. So if you do these on a monthly basis, this runs to about $4,000 per year. And then finally, we don't really have a cost estimate for satellite imaging, but the main problem is that it's very, very inaccessible. So that leads us to a problem statement, which is that there is a significant threat from harmful algae blooms or HABs in the Charles River and a deficiency in cost-effective continuous monitoring techniques. So our team strives to bridge that gap by designing and fabricating an inexpensive sensor that is able to address this problem. So I'll begin with a little bit of a technical overview. So with engineering specifications, we developed this in accordance with the needs of the CRWA, and that includes the cost being less than $1,000. It cannot interfere with the environment. It has to be scalable, has a renewable power source, and finally, it's durable and long-lasting. So then I want to go into a little bit about how optical sensing itself works. So the driving principle behind UV visible spectrometry is spectrometry itself, which is defined as a measurement of interactions between light and matter to classify a compound. So to break this down a little bit, I have an example on the right side showing the green leaf. So when we have visible light hitting this leaf in the form of the rainbow arrow, all that is reflected and what we see is just the green light. So we can apply this principle similarly to classifying compounds such as cyanobacteria, as seen in the chart on the bottom right, which shows its relative absorption as a function of wavelength. So by identifying certain peaks, we can actually figure out what is present in a water sample. And the way we do that is through shining a light through that water, and then the signal that we receive at the other end will be an indicator of what compounds were present in that sample. And we do that using an electrical component called photodiodes, which are sensors that convert light into electrical currents. And to talk a little bit more about that, our configuration in our sensor itself is an LED light, which is a specific color or wavelength, and that light is transmitted and received by the photodiode receptor, which reads in the data and is able to determine what wavelength of light was present, and then therefore classify what compound was present in the sample in between. And then both of these are connected to a PCB or printed circuit board that serves as a computer to collect and analyze data. Okay, and then another big part of our project was the docking station itself. So the sensors will be attached to the docking station, and the docking station will also house the display system, which is essentially a screen that the user will be able to interface with. The docking station will also hold a solar panel and allow for either handheld or continuous monitoring. So now I'll go into results, and I want to preface this by saying that engineering senior design operates on a slightly different timeline. So these slides were due this past Wednesday, but our physical product is not due until next Friday, so naturally they are not done yet. So this is a reflection of what we have done as of last Wednesday. Okay, so to begin, I'll go through this relatively quickly, but this is just an overview of some of our initial spectrometry experimentation. I'm happy to talk about this later, but for the sake of time, I'm just going to keep going. This is a picture of some of our electronics. On the left, we see the sensor itself being tested, and on the right is our LCD screen. For the sensor housing, this is a computer-aided design model of what we wanted it to look like, and we were able to create it using 3D printing into these two right here. For the docking station, this is our initial conception of what we wanted as a drawing, and then we were able to create very preliminary prototypes of it using just foam boards. And then instead of foam, we will actually be using HDPE, which is a form of plastic. And this is my teammate Charles cutting it to shape. And this is some of the pieces that have since been assembled as of this past week, which will look something like the foam board prototype. As for the sensor, this is my teammate Ava working with a UV vis spectrometer. And then we collected cyanobacteria samples, and then we're able to test it using the photodiode and LED assembly using blue and green light as seen here. And then a quick financial analysis of our overall project. So the global market for water quality monitoring systems is fairly large, and it's a growing one, so there's certainly a market for these products. Each sensor came out to be about $275, but we wanted 3 sensors plus a housing for the sensors, so that comes about $850 total, which is still well below our original budget of $1,000. And then for conclusion, I will summarize our outcomes. So we were able to design and fabricate the sensor housing, docking station, and the sensor itself. And it's significantly more cost-effective and accessible compared to alternative options. And it's able to hopefully detect HABs specific to the Charles River. And some future work includes discussing results with the stakeholder, determining effective lifetime, expanding sensing capacities, and designing and testing in other locations beyond the Charles River. So thank you to everyone for coming. I would also like to thank my team and our advisor, Professor DeBella, in the audience. And a huge thank you as well to the Kilachand Honors College, especially Dr. Fish for helping me prepare for this presentation, and the Keystone Planning Committee for making this happen. And I will open it up to questions. Thank you.
So you mentioned in one of your future directions that you would meet with an investor or a stakeholder and implement any suggested changes just based on what you've done now. Are there any improvements that you think people might find desirable in the future?
Yeah, absolutely. That's a really good question. So one of our initial goals for this project was to be able to detect E. coli, and that was a major concern for the CRWA. So our initial testing shows that we aren't able to accomplish that in this given time frame, but that's something that we definitely want to look at in the future. And also, there's different sensing capacities to give a better overview of like the health of the river, such as like turbidity, CO2, pH levels, things like that. So just like expanding the efficacy of the system beyond what we are capable of doing right now.
Hi, thank you for a wonderful presentation, Kathy. I was just wondering, like, how this would be implemented? You said it was handheld, but I was imagining for some reason that it would be like placed in the river. Can you tell us more about that?
Yeah, so just to clarify, so yeah, sorry about that. So it's either handheld or just continuous monitoring. So if we go back a little bit to the housing itself, so it'll be essentially on shore and it'll have, like you can take out the sensors for handheld operation or just leave them in there for continuous monitoring. They're solar powered, so it's able to do that continuous monitoring. But it'll basically be like at the shore, kind of just situated at that place. So in place, and we don't really have to take care of it like all the time.
Follow-up question to that then too. You said the docking system for the materials that you chose, it was a type of plastic.
Yes.
Is that based on the durability, and do you have any concerns about like microplastics entering the river?
Yeah, that's a really good question. So the reason that we chose plastics was for durability as well as just like waterproofing. I think that'd be a really good future direction as well to look more into sustainability because that's what our project is ultimately targeting. So yeah, definitely looking into like more sustainable materials as well. But this was just more based on like what was available to us and like within budget, unfortunately.
Thank you, Kathy. This was so interesting. Can you talk a little bit more about, I think in your conclusion slide, you talk about expanding sensing capabilities. Sorry, yeah, here. Would that imply a different model or would it be the same model with like different like coding?
Yeah, so it would be a slightly different model, primarily with the LEDs and then also the photodiodes that we use. So one of the designs features of our product that I didn't quite mention is that it's modular. So each of the sensors can be taken out and replaced. So the idea is that we'll be replacing the entire sensor itself in the docking station to be able to have these like expanded sensing capabilities.
No other questions? I have a question. As far as the future of this project is concerned, with your graduation impending, what then happens with this project? Does it get passed down? Would you continue to work with them? Or what happens?
That's a great question. So after we graduate, I think we've like discussed this as a team. This is not something that our team will be taking forward, but with a lot of engineering senior design projects, there is an opportunity to pass it down to the next year. So we'll be handing off all of our documentation, and if there's a team that's interested in continuing it, they'll be able to do that pretty easily for the next year. Yeah.
Thank you so much. We'll move on next.